This is an example of line, surface, and volume integrals. What I've got is a path, and in this path I'm in the xy plane, and I'm going from looks like 2, 0 up this arc at 60 degrees, and then I'm going to come back down to the origin, and I'm going to go back to where I started. And so it's a closed path, and I'm going to calculate the circulation of this vector field, which is not shown in the figure. And the vector field has components in the rho direction and the z direction. And so I want to find that circulation. So remember that the circulation is given by this integral here. So we're going to do a closed line integral over L, the path L, right, of A dotted with dl. That's what we're looking at trying to solve. And you see in the figure that I've labeled the 3 segments. There are definitely 3 different segments there, and I've labeled them 1, 2, and 3, and I've circled them. And so if we want to calculate this integral around this closed path or this closed contour, what I can do is find the integral for piece 1 of A dot dl, okay, plus, of course, then the second piece of A dot dl plus the third piece of A dot dl. Okay, and let's remind ourselves what the differential displacement dl is in cylindrical coordinates. I'm going to use cylindrical coordinates here because I've got this, this radial component to this. So what I'm going to remind ourselves of is that the differential displacement is d rho times a unit vector in the rho direction plus rho d phi times the unit vector in the phi direction. That's because phi is an arc, so you have to multiply by the radius, plus dz times the unit vector in the z direction. Okay, so we're going to keep that in mind. And as we solve these integrals, we're going to keep the following question in mind. What is changing? So if you can answer this question, you're in good shape as we go through this. If you can answer that question, you're in good shape, not only for this problem, but future problems and future chapters and actually in the entire course. So we want to keep this in mind. What is changing as we go through this? So let's look at piece 1. Piece 1 is I'm going from x equals 2 up this arc, right, to make a 60-degree angle with the x-axis. All right, so we'll ask ourselves, what is changing along that path? Is the radius changing? No. Is z changing? Well, no, z actually does not play a factor in this because I stay in the xy plane. So the only thing changing here is phi. I was at an angle 0, and then when I stop this path 1, I'm at an angle of 60 degrees, or pi over 3. So phi is changing, so phi changes. So the displacement vector, differential displacement, is simply, right, rho d phi times the unit vector in the phi direction. In other words, d rho is 0 because there's no change in rho, and dz is 0 because there's no change in z. So this is all I'm left with. So my integral then, A dot dl becomes, I've got A is here given in the problem, so this is rho cosine phi A rho plus z sine phi az dotted with dl, and we said that dl is rho d phi times a unit vector in the phi direction, right? Okay, and phi, what's changing. We said that phi is going from 0 to 60 degrees, or pi over 3. So I'm going to integrate that from 0 to pi over 3. All right, so now I have to do this dot product. Right, well, the dot product obeys the distributive property, so I can distribute this in. Now, a phi, the unit vector in the phi direction, is orthogonal to a rho, the unit vector in the rho direction. So a rho dotted with a phi is 0. And similarly, a phi dotted with a z, those are orthogonal as well. Those directions are orthogonal. So a phi dotted with a z is also 0. So this integral is just 0. You gotta understand that those unit vectors are all orthogonal. So when you take the dot product of any of any of those unit vectors, then you get 0. All right, moving along. Path 2. So we're going to integrate path 2, a dot dl. Okay, and we're going to ask ourselves, what is changing on path 2 when I go down this line? The angle is not changing now because the angle is fixed at 60 degrees. Z is not changing because I'm in the xy plane. The only thing that's changing is the radius. The radius is going from 2 to 0. Okay, so I'm going to be integrating over the radius going from 2 to 0. The order matters here, not 0 to 2, 2 to 0, because again, it's the directed distance, right? From 2 to 0. So 2 to 0, then I've got A. A is rho cosine phi A rho plus Z sine phi AZ dotted with dl. So what is dl now? And we just said that rho is the only thing that's changing. So d phi is 0, dz is 0. Z doesn't change, phi doesn't change. So this is just d rho times the unit vector in the rho direction. Okay, so now I distribute that in. And when I distribute that in to the z, AZ component, those two are orthogonal, and so they make 0. But when I distribute it into the A rho component, those are parallel, and A rho dotted with A rho is just 1. So this becomes rho is 2 to 0 of rho cosine phi d rho. Again, where did the A rhos go? Well, A rho dotted with A rho is 1. So they're gone. They make 1. AZ dotted with A rho is 0 because they're orthogonal. So now I've got this integral to solve. Cosine of phi, as far as rho is concerned, is a constant. So I can bring that out of the integral. So I've got rho d rho. So this is cosine of phi. What is phi? Phi is pi over 3, we've already said. Right? And then when I integrate rho d rho, I get 1/2 rho squared from 2 to 0. So this gives me, when I plug in the 0, I get 0, and then minus what I get when I plug in the 2. So this gives me 2 squared is 4, divided by 2 is 2. Cosine of pi over 3 is 1/2. So this gives me minus 1. Okay. Now segment 3, I'm going from the origin to x equals 2, right? So I've got segment 3, a dot dl. And I'm going to ask myself, what is changing along segment 3? Well, the radius is changing. I'm going from a radius of 0 to a radius of 2. Is phi changing? No. Phi stays fixed at 0 degrees on segment 3. Is z changing? No. So I know I'm going to be integrating. Rho goes from 0 to 2. Notice that it's different now. It's switched because I'm going outward from 0 to 2. Now I've got, again, my vector field, rho cosine phi A rho plus z sine phi az dotted with what is dl? Well, we come up here and we already said that rho is the only thing that's changing. In other words, d phi is 0, dz is also 0. So this is just d rho a rho, like that. Okay, now I distribute the a rho, the dot product in. A rho dotted with a rho is 1. Okay, because they have unit length. And so this is rho cosine phi d rho. And then when I distribute the dot product into the z term, az dotted with a rho is 0 because those are orthogonal unit vectors. So this is my integral that I have to solve. It's similar to the last one. And cosine of phi is a constant as far as rho is concerned. And so I'll bring that out of the integral, and the angle phi now is not pi over 3, but it's 0 along segment 3. So this is cosine of 0 times rho goes from 0 to 2 of rho d rho. So when I integrate that, cosine of 0 is 1, and I integrate rho d rho, that's 1/2 rho squared, from 0 to 2. So this is just 2. And so, you know, the question asked me to find the circulation. So as I go around that entire edge, the circulation of A around that edge. So I add up these three components, 0 plus -1 plus 2, and I get 1 as my final answer.